Hello everyone, this is Gayatri Priya, Assistant Professor in the Department of ECF, RMD Engineering College. In today's session of analog electronics, we're just going to discuss about what are the factors which affects the frequency response of amplifiers. So before getting into this, we should know why the frequency response has the y-axis, that is the gain is being measured in decibel. So actually we know that unit of sound is decibel or dB or here we are having a small d and capital B. Okay, so actually that a capital B indicates Alexander Graham Bell. For standardization, we are just utilizing G is equal to, that is gain is equal to log to the base 10 of P2 by P1, that is power 2 by power 1 in Bell, right? For practical purpose, we used to define this dB as 10 decibel, that is equal to 1 bell, right? Okay, therefore, G is equal to 10 log to the base 10 of P2 by P1. So if I want to measure the gain in dB, okay, that is if I want to measure the voltage gain. If it is power gain, it is going to be 10 log to the base 10. But if suppose we want to measure the voltage gain, okay, so actually how we can write power is equal to V into I. Okay, we can say it as V into I, or we can say it as V square by R or I square R, whatever it might be the thing. If I am making V square by R, that is V2 by R2 whole square by V1 by R1 whole square. If R1 and R2 are going to be the same, I can write it as V2 by V1 whole square. So, if I am taking the power value and multiplying by the prefix 10, it will become 20. 20 log to the base 10 of V2 by V1 in dB, right? So here we have given the explanation for that also. And also we know that many statistics have mentioned that the hearing capability of a normal human ear is only 70.7 percentage. Even though we are communicating 100 percentage of information, many noises will be incorporated with that so that we could not get 100% exact output. The minimum acceptable frequency is going to be 70.7. How it could be 70.7? If I want to convert the 70.7 into dB, I'm just utilizing the voltage gain AV equal to 20 log to the base 10 of 70.7 out of 100. If we convert this, we'll be getting minus 3.011 dB. And that's why we prefer to express the frequencies, that is the corner frequencies, with respect to 3 dB. So 3 dB down the line we will be drawing. Okay, that is from AV max, will be coming down 3 dB. Okay, that down is only because of this negative sign over here. This is the frequency response of an amplifier. Okay, so what we are saying in the sense, this is going to be 3 dB, that is 70.7 percentage of the maximum voltage gain. We can obtain the maximum voltage gain only at the mid frequency, and therefore it is indicated by AV mid. Okay, so AV mid will be equal to 70.7 percentage. If I consider AV mid as 1, okay, this point would be equal to 0.707 times of AV mid. Okay, so exactly 3 dB down. So if I draw a horizontal line, that will cut the frequency response at 2 points, and if we extend it along the x-axis, these are called the corner frequencies or half power frequencies or cutoff frequencies. In particular, this is called lower cutoff frequency and this is called upper cutoff frequencies, right? So why it is called half power frequency in the sense at exact at this frequency we will be getting 50 percentage of the output power at the mid frequency region, and that's why these are called corner frequency or cutoff frequencies or 3 dB frequencies. Quite interesting is that the bandwidth is going to be the difference between the upper cutoff frequency and the lower cutoff frequencies, that is f2 minus f1, right? and this is the gain in various frequency regions. Okay, so the mathematical expression for the gain at the lower frequency can be given like this, and for the upper cut of upper region can be given like this. Okay, so based on that we have drawn a sum. Okay, so these are the factors which affects the bandwidth of RC coupled amplifier. The first one is going to be coupling capacitor C1 and C2. Second one is bypass capacitor. And the third one is internal capacitance or stray capacitance. First, let us see what is the effect of coupling capacitors. We know that the coupling capacitor normally blocks DC and allows only the AC signal. The reactive component can be given as Xc is equal to 1 by 2 pi Fc. So as already discussed, if Xc increases, automatically it will reduce the frequency and vice versa, right? So what happens in the sense this because of this the voltage drop across them will be increasing with reduction in the frequency. Because of that voltage drop, what happens in the sense both the output voltage as a result the gain will also get declined, and that's why at the lower frequency region we are getting a very lower gain compared to that of the mid frequency region. Next, coming up for the effect of bypass capacitor. So we know that the bypass capacitor, here it is connected parallel to that of the emitter resistor. At medium frequency and high frequency alone, this bypass capacitor will play a prominent role. That is, it can be replaced by a short circuit. At a higher frequency, the roll off in the gain is only because of the internal capacitance or the stray capacitance is present. Okay, so because of this, what happens? It will reduce the amplifier gain and thereby it will introduce some amount of phase shift. So these are the interelectrode capacitance in your BJT, and these two are the interelectrode capacitance of a JFET amplifier. So hope you understand this session. Thank you.